Have you ever watched a flock of birds shift direction in perfect unison, or seen ants march in a precise line to carry food? That's swarm intelligence in action, simple rules leading to complex, coordinated behavior. Today, we're diving into how researchers use formal specifications to design self-organizing robot swarms that can form specific shapes, like a puzzle coming together piece by piece. Let's start with the basics. Imagine a group of robots tasked with forming a shape, say a square. But how do they know where to go? The answer lies in three key states: empty, partial, and complete. At the beginning, the shape is empty. No robots have joined yet. Think of it as a blank canvas. As robots start moving and localizing near a central point, the shape becomes partial, like the first few pieces of a puzzle snapping into place. Finally, when all robots are in their correct positions, the shape is complete. The puzzle is finished. But how do the robots know their roles? Here is where shapeDimension comes in. This variable defines the size and contour of the target shape. For example, if the shape is a 2x3 grid, the shapeDimension would be 2 multiplied by 3. The robots use this value to calculate where they need to be, like following a blueprint. Now let's break down the process. Initially, all robots are in a random or unlocalized state, like explorers wandering aimlessly. When one robot finds a seed, robot near the origin, the starting point, it joins the shape. This triggers the robot join schema, updating the shape's state from empty to partial. As more robots join and localize, the shape gradually fills in, until every robot is in place and the shape becomes complete. But what if something goes wrong? The research also accounts for errors. For instance, if a robot is already moving or faulty, the system logs this as an error outcome. These are categorized using a report type with labels like alreadyMoving, alreadyFaulted, or alreadyCompleted. It's like a robot's progress report, ensuring the system can handle hiccups without crashing. The magic here is the use of schemas, formal rules that define how the system transitions between states. Think of them as step-by-step instructions for the robots. For example, the move schema combines successful movement with error checks, while fault handles robots that stop due to issues. These schemas ensure the swarm operates reliably, even in complex scenarios. Now let's get technical. The researchers used the Z specification language, a formal notation for describing systems with mathematical precision. Z allows them to define states, transitions, and constraints in a way that's unambiguous and verifiable. For instance, they model the robots' stationary state, their unlocalized phase of random movement, and their localized phase when they lock into position. By encoding these rules in Z, they create a framework to predict and debug potential issues before building physical robots. This approach isn't just theoretical. Simulations based on Z models can test scenarios like overcrowding in one area, or the system getting stuck in an incomplete state. This saves time and resources, as engineers can refine the logic digitally before deploying hardware. Why does this matter? Formal specifications like these provide a blueprint for building robust swarm systems. They help engineers predict how robots will behave, troubleshoot issues, and scale up to more complex tasks, like pathfinding or foraging. Imagine a future where robot swarms assemble structures on Mars or clean up ocean plastic, all guided by these precise rules. So next time you see a flock of birds or a school of fish, remember, it's not magic, it's math. And with research like this, the future of swarm robotics is looking more organized and more amazing than ever. Want to see how this works in action? Hit subscribe for more deep dives into the science behind the tech.